Hi friends, welcome to our next video. In this video we are going to discuss about rest of the topic of fluid mechanics, all equations and facts. In this video mainly we are going to discussing dimensional analysis, impact of jets, hydraulic turbine and hydraulic pump. First of all, dimensional analysis. In this we can see that velocity potential can be written as its dimensional analysis is L square t raised to minus 1, and for stream function it is L square t raised to minus 1, acceleration it is L t raised to minus 2, vorticity it is t raised to minus 1. Total number of variables influencing the problem is equal to the number of the independent variables plus 1, 1 being the number of dependent variable. Next is Buckingham's pi theorem. It states that if all the n variables are described by m fundamental dimensions, they are grouped into n minus 1 dimensionless pi terms. Selection of 3 repeating variables from the geometry of flow, fluid properties and fluid motion. Geometric similarity means that similarity of shape. Kinematic similarity means similarity of motion. Dynamic similarity means similarity of forces. Now, this is a table, number, equation and significance. First number is Reynolds number. Its equation is Fi by Fv equal to rho Vl by mu. Its significance is that flow in closed conduit pipe. Next number is Froude number. Its equation is root of Fi by Fg equal to V by root Gl, where a free surface is present. Example, waves, spillway, channels, etc., where gravity force is predominant. Next number is Euler's number. Equation is root of Fi by Fp equal to V by root of P by rho. Significant, it is used in cavitation studies. Next number is Mach number. Mach number equation is root of Fy by Fe equal to V by C, where fluid compressibility is important. Last number is Weber number. It is root of Fy by F sigma equal to V by root sigma by rho L. It is used in capillarity or capillary studies. Fi is inertia force, Fv is viscous force, Fp is pressure force, Fe is elastic force, F sigma is surface tension force. Next is Reynolds model law. Reynolds model law means Reynolds number for the model and Reynolds number for the prototype are same. That is REM equal to REP. It means that rho r, V r, L r by mu r equal to 1. Application of Reynolds model. Flow through small sized pipes. Low velocity motion around automobiles and aeroplane. Submarines completely underwater. Flow through low speed turbo machines. Next is Froude's model. Froude's model law is also same, that is Froude number for model and prototype are same. That is VR by root LR GR equal to 1. Applications of Froude model law. Open channels, notches and waves, spillway and dams, liquid jet from orifice, ship partially submerged in rough and turbulent sea. Next topic is impact of jet. Very important. Impact of jet means the force exerted by a jet on a plate which may be stationary or moving. The force is obtained from impulse momentum equation. Force is obtained from Newton's second law, that is impulse momentum equation. Now we are going to see different cases of impact of jet. First is force exerted by a jet on stationary plate. In that, if the plate is vertical to the jet, that is the first case. Here stationary plate, also the plate is vertical. Jet strikes normally to the flat stationary plate. You see the figure. By seeing this figure, you can identify that. Force exerted by the jet normal to the plate. That is Pn is equal to rho a v square. Fn is equal to otherwise rho a v square. A is equal to area of jet, v is velocity of jet. Next is when the plate is inclined. Plate is stationary, also plate is inclined. You see the figure? In that, force exerted by the jet normal to the plate Pn, otherwise Fn. Here it is written as Pn, that is force exerted by the jet normal to the plate. Pn equal to rho a v square sin theta. Q1 equal to Q2 by Q by 2 into 1 plus cos theta. Q2 is equal to Q by 2 into 1 minus cos theta. By taking the two equations, Q1 by Q2 is equal to 1 plus cos theta by 1 minus cos theta. Px is equal to rho a v square sin square theta. Py is equal to rho a v square sin theta cos theta. When the plate is curved, jet striking on a symmetrical stationary curved plate. You see the figure? Force is rho a v square into 1 plus cos theta. In this, plate is stationary, also plate is curved. Force exerted by a jet in this direction of flow on a curved vein is always greater than that force exerted on the flat plate. Next is angle of deflection. Angle of deflection is nothing but 180 minus theta degree. Next case is when the plate is not stationary, it means that the plate is moving. Force exerted by a jet on moving plate. First case in that is plate is vertical to the jet. Force exerted by the jet on moving flat plate normal to the jet. Moving plate also normal to the plate. Plate in that equation is nothing but work done per second. Before that, force, that is Pn equal to rho a v minus u the whole square. Work done per second W is equal to Pn into mu u, that is rho a v minus u the whole square into u. Next case is plate mounted on a periphery of wheel. Jet strikes on series of flat plate mounted on a periphery of wheel. You see the figure. By seeing this figure, we can identify that variation or difference. In that force equation is Pn equal to rho a v into v minus u. Okay, then the work done in this case is Pn into, otherwise force into u, equal to W equal to rho a v into v minus u into u. Efficiency of work done of wheel, that is eta equal to 2u into v minus u by v square. Point to remember, when periphery or peripheral velocity will be half of the velocity of the jet, that is u equal to v by 2, then efficiency will be maximum, that is eta max is equal to 50%. Curve plate when plate is moving. You see, this is a not stationary, plate is moving, at the same time plate is curved. In that, you see the figure. Force equation is P equal to rho a v minus u the whole square into 1 plus cos theta. Work done by the jet on the plate per second equal to, in this case, work done equal to W equal to rho a into v minus u the whole square into u into 1 plus cos theta. Force exerted by a jet on hinged plate is the next case. We have a figure there. Force due to the jet of water normal to the plate Pn equal to rho a v square sin into 90 minus theta. That is rho a v square sin 90 minus theta. For equilibrium, sin theta equal to rho a v square by W. Next chapter is very important and very popular chapter, that is hydraulic turbine. What is hydraulic machines or hydraulic turbines? Hydraulic machines are defined as those machines which convert either hydraulic energy into mechanical energy or mechanical energy into hydraulic energy. In that, two types we know that, pump and turbine. What is turbine? We are going to discuss what is turbine. Turbine is nothing but the hydraulic machines which convert hydraulic energy into mechanical energy. That is turbine. Different types of, different kind of efficiency of turbine are there. One is hydraulic efficiency, second one is mechanical efficiency, third one is volumetric efficiency, and last one is overall efficiency. Hydraulic efficiency eta H equal to power developed by the runner divided by net power supplied to the turbine entrance. Mechanical efficiency eta mech equal to power available at the turbine shaft divided by power developed by the runner. Next is volumetric efficiency eta volume. Eta volume equal to quantity of water actually steering the runner by quantity of water supplied to the turbine. Last efficiency is overall efficiency eta O is equal to shaft power by hydraulic power. Then eta O equal to eta hydraulic efficiency into mechanical efficiency into volumetric efficiency is the overall efficiency. Overall efficiency is the product of hydraulic efficiency, mechanical efficiency and volumetric efficiency. Next is classification of turbine. Classification of the turbine. Impulse turbines, they have only kinetic energy at inlet. Examples of impulse turbine are Pelton wheel, Bangi turbine, Joule turbine, Turbo impulse wheel. Important is Pelton wheel only. And this is the one of the classification based on the energy at inlet. First is impulse turbine. Second is reaction turbine. They have kinetic energy and pressure energy both at inlet. Examples of reaction turbines are Francis turbine, propeller turbine, Kaplan turbine, Thomson turbine, etc. Next classification is classification of turbine on the basis of type of flow within the turbine. Tangential flow turbine. Example is Pelton wheel, Turbo, impulse wheel. Next is radial flow turbine. Radial flow turbine example is Francis turbine, Thomson turbine, etc. Axial flow turbine example is mentioned here. See this. Next is mixed flow turbine. You see that turbine is classified on the basis of type of flow or tangential flow turbine, radial flow turbine, axial flow turbine, mixed flow turbine. Next classification is based on the specific speed. Very important. For Pelton wheel, specific speed is between 10 to 35 mg. In mg's unit it is mentioned there. For Pelton turbine, it is between 10 and 35. For Francis turbine, the specific speed is between 60 to 300. For Kaplan and propeller turbine, specific speed is between 300 to 1000. Classification of turbine on the basis of value of head speed. For Pelton wheel, it is about 250 meter. If the head is between 60 and 250 meter, that turbine is Francis turbine. For Kaplan and propeller turbine, the head speed is below 60 meter. Head is below 60 meter. This is analysis of turbine, that is work done, efficiency, etc. Speed ratio like that. First is work done. Its equation is, remember that W is equal to rho Q into VW1 plus VW2 into U. And it is written as rho A V1 into V1 minus U into 1 plus K cos phi into U. Okay. Now efficiency of Pelton wheel. Nozzle efficiency eta nozzle equal to kinetic energy of jet per second by water power at the base of nozzle. Next is hydraulic efficiency. Hydraulic efficiency value is runner power by kinetic energy per second. Its value is mentioned there. Next is mechanical efficiency, we that eta mech is equal to shaft power by runner power. And after this, very important terms are velocity of jet. That is V1 equal to CV into root 2GH. And CV value is between 0.97 to 0.99. Next is speed ratio, very important. Speed ratio value KU equal to U by root 2GH. Okay. Next is jet ratio M. That is M is equal to D by D. D means diameter of wheel by jet dia. Number of bucket equation. That is Z equal to D by 2D plus 15 equal to M by 2 plus 15. Number of buckets is between 18 to 25. Some of the points are, it is tangential flow impulse turbine. It is high speed low discharge turbine. The bucket of Pelton wheel is, these points are based on the Pelton wheel. Okay. The bucket of Pelton wheel is double in shape. The jet of water impulse at the center of the bucket and deflects through 160 degree to 170 degree. Advantages of having double cup shaped buckets is that axial thrust neutralizes each other. If P is the power developed by the Pelton wheel, when working under the head, having one jet only, the power developed by the same wheel will be N into P. If N jets are used under the same head. And this is the analysis of Francis turbine. This Francis turbine, all these terms are also we are going to learn. That is work done, degree of reaction. Next is flow ratio, speed ratio, discharge through the turbine. You see, flow ratio is 5. Psi is equal to Vf1 by root 2gh. Speed ratio Ku equal to U1 by root 2gh. Discharge through the pipe Q equal to pi D1 B1 Vf1. Some of the points in this Francis turbine is that it is inward radial flow reaction turbine. Scroll casing is used to evenly distribute the water along the periphery and maintaining the constant velocity for the water. The basic function of draft tube is to convert kinetic head into pressure head. The angle of straight divergent type draft tube should not be more than 8 degree. Otherwise, eddies will be formed, efficiency will be reduced. Now, common important facts are discussing. First is Kaplan turbine. If the velocity triangle and calculation of efficiency is similar to Francis turbine, okay, all equations are similar to Francis turbine. It is axial flow reaction turbine. Runner of Kaplan turbine has 4 to 6 blades, and all these points are very important. Next is about diagonal turbine. Please read this. Blades are adjustable. It can be used to turbine as well as pump, but which diagonal turbine? Next is tubular turbine. It is have adjustable or non-adjustable runner blades. Head range is between 3 meter to 15 meter. Scroll casing is not provided. Next is performance of turbines or unit quantities. Unit speed NU, very important. NU is equal to N by root h. Unit discharge QU equal to Q by root h. Unit power is equal to PU equal to P by H raised to 3 by 2. Next is specific speed or specific number. Very important. This definition must known for every mechanical engineer. It is a speed in RPM of a turbine geometrically similar to the actual turbine but of such a size that under corresponding condition it will be developed unit power when working under unit head. That is NS. What is that? Specific speed equal to N into root 2 P by H raised to 5 by 4. Point to remember, specific speed is not a dimensionless parametric dimension is M raised to 1 by 2, L raised to minus 1 by 4, T raised to minus 5 by 2. Dimensionless form of specific speed is called shape number, that is S. S is equal to N root P by rho by G H raised to 5 by 4. Now, very interesting topic, that is model laws of turbines. Some of the model laws are there. Model and prototype turbines are based on the assumption that efficiency of model is equal to that of prototype. But the efficiency of prototype is higher than the model's efficiency, that is scale effect. You see that Q by ND cube model equal to Q by ND cube prototype. The parameter Q by ND cube is called CQ, that is flow coefficient. If the interviewer asks you what is flow coefficient, we will say that CQ equal to Q by ND cube. You see this all numbers, all ratios and all parameters, power coefficient, head coefficient, etc. These are all important. These terms are not studied while in syllabus, but these equations and these coefficients terms are very important. And the last topic is hydraulic pump. After the turbine, we are discussing about hydraulic pump. It is also a hydraulic machine. And centrifugal pump is the reverse of inward flow reaction turbine. It works on principle of forced vortex motion. It is high discharging capacity and can be used for lifting highly viscous liquids. Next is priming. It is an operation in which liquid is completely filled in the chamber of pump so that the air of gas or vapor from the portion of the pump is driven out and no air pocket is left. This term is very familiar. Next is head vs discharge and power vs discharge relationship. See these two graphs. One is head vs discharge, second one is power vs discharge. Different types of pumps based on head, types of pump and range. If the pump head range is up to 15 meter, that is low head pump. If the pump head is between 15 meter to 40 meter, that is medium head pump. If the pump head is above 40 meter, that is known as high head pump. Now, type of pump based on specific speed. If the specific speed is between 10 to 80, that pump is radial flow. And if the specific speed is between 80 to 160, it is mixed flow. And the specific speed is between 180 to 450, that is known as axial flow pump. Next is different efficiencies used in this pump. That is eta manometry. Manometric efficiency is there. Volumetric efficiency is there. Mechanical efficiency is there. And overall efficiency. Overall efficiency means it is a product of manometric, volumetric and mechanical efficiency. Next is different parameters of pump are same as the turbine. You see that work done. What is that? Rho Q V W2 into U2. Okay. Then is static head, manometric head. This is the manometric head equation. See this. And the notations PD, PS, VD, VS, ZD, ZS are mentioned here. And I see speed ratio. Before that, you see this diagram. Mechanical losses, hydraulic losses, and other losses are mentioned here. Okay, speed ratio KU. What is that? U2 by root 2J. Next is flow ratio psi. That is VF2 by root 2J. Some of the points says that for optimum efficiency, impeller should be designed such that valve velocity at the inlet is 0. It means discharge should enter in the pipe radially VW1 equal to 0. That is valve velocity VW1 at inlet. Pump will start pumping only when the pressure head will be greater than or equal to manometric head. Next is specific speed of the pump. Same as that of turbine, okay? Specific speed equation is that Ns equal to N root Q by Hm raised to 3 by 4. For multi-stage pump, Hm equal to total head by number of stage. Now pump in series and pump in parallel. Pump in series, the pump are connected in series in order to increase the head at constant discharge. That is Q1 equal to Q2 equal to Q3. H equal to H1 plus H2 plus H3 etc. Pump in parallel. Pumps are connected in parallel in order to increase the discharge at the constant head. That is Q is equal to Q1 plus Q2 plus Q3. H is equal to H1 equal to H2 equal to H3. Pump is in series, Q is same. If pump is in parallel, H is same. Modal loss in pump are same as that of what? Turbine. See these equations. Remember the equations. By heart these equations. Very important. This is cavitation in pump. The following factors contribute towards onset of cavitation. High runner speed, high temperature, less available NBSH. This is different parameters of operating characteristic or reciprocating pump. You see that Q is equal to Ln by 60. Work done is equal to, for reciprocating pump. Also head against different section head. Slip, equation for slip very important. Q theoretical minus QHL by Q theoretical into 100. Finally we get 1 minus CD into 100. You see this figure, we can see that the graph between head and discharge input to power efficiency. See that. Last one is different points to remember. Friends, please study these 6 points, very important points, which will help you when doing the problem for competitive exams.